I, I guess I need to introduce Dr. Matthew Chambonneau that I have expressed pronunciation. Oh, okay. Great time. I know a lot of people are here. We are both interested in the direction between the semiconductors and lasers. And a lot of people ask me, can we fabricate the silicon in volume fabrication of silicon? And I always told them it's very hard and very tricky. And today we have a very a very pro- professional, yes. Professional and professional Dr. Maxim Chambonneau to introduce the complex laser filamentations for internal structuring of silicon. And he had ever made a lot of very interesting work around this topic, and I have read a lot of papers when I was still a PhD student. So I'm really happy to see him today. I mean, so it's so okay. So
You want the laser point? Like,
I mean,
thank you very much, Zhen-Ze, for your kind introduction, also for welcoming me in this wonderful and hot town city. So this is amazing. So as introduced, my name is Maxime Chambonneau, working at the Institute of Applied Physics. This is in Jena, which I will introduce later on. A very small city, especially when you compare it to Chinese cities. Very small city in Germany. And today, as introduced by Zhen-Ze, I will speak about like how to process or try to silicon internally with laser process. So yeah, this is the title of my talk, and it's before going into the details. All right. So Jena in one slide. So this is as you see here in the very center of Germany, in Europe. This is very small town, so 100,000 people. Yeah, so please don't compare to Beijing. This sounds ridiculous. And despite the fact that it's a very small city, it's quite famous for some scientists who've been there. So Carl Zeiss, who's kind of the inventor of microscopy in the 19th century. So this is the guy on the left. Otto Schott, who's also famous for glass manufacturing, so fabricating some glass, and there is a lot of chemistry involved, so I won't go too much into the detail. And Ernst Haber on the right, so the guy who's famous for the theory behind, and especially for the Haber diffraction limit, which gives you the resolution of some microscopy instruments. So yeah, this is the typical town. So only one large tower, large building. The rest is more historical. And I work especially in the group of Professor Stefan Nolte, whose group is entitled Ultrafast Optics. And we cover different topics, probably so as you hear, including laser functionalization of glasses. So like writing waveguides in glass, or writing Bragg ratings inside fibers, inside like volume glass. We also do some Raman spectroscopy, some additive manufacturing. So basically powder bed fusion for like 3D printing of metals or any kind of material actually. And silicon laser processing, which is a more recent topic connected to what I will present afterwards. But before speaking about what's feasible in silicon, let's recall or introduce for some of you who are not too familiar with the topic, like what is actually possible in dielectrics when you use like ultra-fast laser processing, so like femtosecond, possibly some picosecond laser passes. So basically, it's an extraordinary tool because you can do many things, including Here on the left, fiber optics, so like inscribing volume fiber bright ratings for spectroscopy, for instance, but also for filtering out some wavelengths in fibers. You can do, you can also write some micro channels inside a glass chip to do some lab-on-a-chip tests. So basically you take a blood droplet, put it there, and then the system can analyze what kind of disease you have, if you have some. You can also do some micromechanics by playing on the mechanical properties of some thin glass plates, which act then as a micro cantilever. You can, as developed by Microsoft, you can do some data storage with so Zhen-Ze, you just mentioned this, like Peter Kazansky's group, like those 5D memories, just to store a lot of data. And basically in a tiny piece of glass, they can store the Holy Bible, basically. You can do some glass crystallization, like for like creating some anisotropy in glass for second harmonic generation, for instance. You can do surgery, and then there are this whole set of industrial applications, which is extremely relevant for the industry. So like ultrafast laser drilling, ultrafast laser cutting, which is a video from Prof in Germany. And also you can weld two work pieces together, but you just shine the light and that's it. Your two work pieces become only one work piece. So this is quite nice. And then you have some more exotic, I would say, exotic applications like super densification. So basically this consists of like micro explosions in the bulk of the glass. And with that, you can produce some new polymorphs. So some new phase of the material, which were not observed before. Like you need some very high pressure, very high temperature. And this is what femtosecond laser pulses can achieve in glass. And finally, from an institution closely connected to mine, Fraunhofer IOF, you can do some waveguide writing actually in glass and do potentially some quantum circuits in a tiny piece of glass. So sorry if so this was designed basically for some of my students. So I will recall some basics here. So how can we explain the success of ultrafast laser processing in glass? Well, basically, there are two important parameters. In that case, the first one is related to the spectrum, so some wavelengths. And when you want to process a material, basically you got to be to use a wavelength which is closely connected to the band gap of the material. So e.g. here. So you ensure that you have, instead of linear absorption, you have multi-photon absorption inside the material. And as a result, when you compare the linear absorption here and the two-photon absorption here, well, basically you can see that you can have highly confined energy deposition inside, at least glass, inside glass. So the interaction takes place in a very tiny volume. This allows for an increased degree of control on the kind of modifications you produce. But of course, when we speak about ultra-fast laser processing, we have to give some words about what happens in the time. And this is like a time scale. So let us consider first a pulse of like 100 femtosecond, which is not too short, but not too long either. And then let's have a look to some mechanisms which occur. Basically, the first mechanism which can occur is the propagation. So this occurs during the pulse, basically. And this is governed by Maxwell's equation. And simultaneously, or almost at this time scale, you get some ionization taking place with different, you can account for various mechanisms. Here I represent in multi-photon absorption and avalanche, but you can consider like recombination, tunnel, ionization, many things actually. And then on the other hand, when when you take a look to what happens on a very long time scale, so after a few tens of picoseconds, typically, what happens is the material response. So you get a set of thermomechanical events, including the launch of shock waves. So this is governed by the hydrodynamic equations. You got heat diffusion, which is governed by Fourier law. And finally, you get some resolidification, which occurs inside your solid. And from in between, you have this electron phonon scattering, which means that the electrons can be, like the energy gained by the electrons is then released to the ions. And this is why at those ultra fast or ultra short time scales, you can clearly separate the causes of the energy deposition from the consequences which are related to the material response. So you get a full control on that. And to give you an example, so this was done in my institute before, like a long time ago, actually. When you compare some holes that you want to produce on some material, then with ultra-short laser pulses, you can see it's a pretty clean hole. While when you use long pulses, then there is like a lot of heat-affected zone and those shock waves which occur during the pulse. And as a result, this is the tip of a match. And when you use ultra-short laser pulses, you can write whatever you want on this because the heat load is not sufficient to burn it. However, when you use long pulses, then your matchstick becomes burnt. Okay. And now the question is, why should we extend this kind of technique, so ultrafast laser inscription, to silicon? Well, there are actually many reasons for that, but the first one is for academia, just to understand the response of narrow gap materials under extreme conditions. And with that, we could determine some parameters which are extremely difficult to access with other techniques. So like ionization, the ionization dynamics, like how plasma form inside narrow gap materials such as silicon and so on. The second reason is, of course, when we speak of silicon, we have in mind directly like the Silicon Valley in the US or like all those high-tech companies. And this is, of course, related to the electrical properties of silicon, which are like a synonym of industrial applications. And to fabricate some silicon device, there are some techniques right now. So typically those lithography methods, such as silicon on insulator, SOI. The problem of these methods are that these are like 2D methods. So if you want to fabricate a 3D structure, you got to process like layer by layer. This takes time, and this gives rise to some costs, right? And also, yeah, you need some clean environment. Like basically when you fabricate something, if some dust particle comes into whatever you want to process, then basically you can process what you were fabricating, you can throw it away and just start again from scratch. On the other hand, if one can develop some laser inscription inside silicon, then one could fabricate some 3D structures inside the material. It is flexible, it is fast, and it is contactless. So like numerous advantages to develop ultrafast laser inscription to silicon. And the last reason why we should extend this technique to silicon is for economy. When you look to all the markets where silicon is involved, so here are a couple of examples. So silicon photonics, of course, quantum technologies, ultrafast microelectronics, optical sensors, photovoltaics, and so on. And those are constantly growing markets. When you look to the investors, like the investment which is done on silicon technologies, it's constantly growing. Okay, so let's do that, right? Well, can we just simply transfer it? So as I mentioned before, because of the band gap, which is shorter, we need to go to the infrared. And this is now possible. There are some reliable and stable infrared laser sources for producing some ultra short laser pulses. The problem is that we also need some optics and detectors, which are usually quite costly and less efficient in the infrared compared to the visible. So the best performing infrared camera is like 10 micron pixel pitch. When you compare it to the pixel size of your smartphone, this is below 1 micron. So there is something to gain. But the main difficulty when you want to transfer ultrafast laser writing from glass to silicon, the main problem is that silicon is a medium where everything gets extreme. And by extreme, I mean, so there is extremely low band gap, so around 1.1 EV electron volts compared to fused silica. So here on the left, you get silicon, on the right, you get fused silica. Fused silica is about 9 electron volt. You get also some high refraction, so linear refraction, just by taking the value for the refractive index of silicon and compare it to glass. You get also some very high group velocity dispersion, which means that as long as you propagate through silicon, then potentially if your pulse is too short, it will be broadened unless you pre-compensate for that. And you get also some extreme nonlinear refractive index, and this will be probably one of the major challenges here, which is about 2 orders of magnitude higher in silicon compared to fused silica. And also, yeah, you can find also these 2 orders of magnitude on the thermal diffusivity of silicon compared to the insulator, which is fused silicon. So everything gets extreme. And now the outline of my talk is the following. So first, I will show you, so the whole talk is about some overview about the topic. So I will speak about the works of others and also mine. So first I will introduce the limitations concerning filamentation in silicon. Then some ways that have been found so far to circumvent those limitations and bypass them to process silicon. And finally, I will show you some applications of what can be achieved in the material. Okay, so first, the physics, the limitations concerning filamentation in silicon. Well, as I said earlier, silicon is a medium where you have an extremely high nonlinear refractive index. What does it imply? It implies that there will be a very high Kerr effect, especially when you use ultra-short laser pulses. So Kerr effect will tend to self-focus the beam. And as a counterbalance of this Kerr effect, there will be some plasma defocusing phenomena. So once you focus too tight, at some point, a plasma will be created and the plasma will defocus the light. And then you get these 2 competing ingredients. So self-focusing occurs and then the plasma is formed. So some plasma is formed, it defocuses the light, then the light is refocused by Kerr effect and so on and so forth. So you get those filament dynamics. So this is like the filament regime, the filamentation regime, I should say. And this is basically this was studied in glass before, or in glass and also, of course, in air. But in silicon, it's pretty new. So what can we learn from the studies of other? And this is actually why I was here last week, actually not in Beijing, but in Tianjin. There was a conference on filamentation, and they showed that filamentation is quite advantageous regime if you want to do different things, including LiDAR, spectroscopy, terahertz wave generation, for clearing air waveguides, and also it was recently demonstrated by this French group that you can actually guide lightning. So this is pretty impressive. And the thing is, in silicon, filamentation has two major effects. The first one, illustrated on the top, is that you can see that. So this is the fluence inside the material as a function of the optical path for different input pulse energies, and you can see that the focus tends to shift upstream the laser when you increase the input pulse energy. So this is the first limitation, which is the nonlinear focal shift. And simultaneously, you also have this this phenomenon, which is called intensity clamping. So something quite known for people working on filamentation for decades. This is the fluence inside the material, inside silicon, as a function of the input pulse energy. And you can see that after a certain threshold, which is dependent on your conditions, then the energy deposition, so the maximum fluence in silicon, tends to saturate. What does it mean? It means that if you want to deposit more energy by just putting more energy at the entrance of your wafer, it will fail. And when you take those two consequences together, one can easily conclude that basically there is some delocalization of the energy deposition, which occurs preferentially towards the prefocal region, and then increasing the laser energy will be just a bad strategy if you hope to modify silicon. So the main difference, to conclude on that, the main difference between silicon and dielectrics is illustrated here. So this is probably the most important figure of my talk, actually. What I want you to take home. If you display the maximum fluence in the bulk of the material as a function of the input pulse energy, you can see that for the electrics, the filamentation regime can be achieved with this intensity clamping here, but you are above the damage threshold, so above the modification threshold, meaning that you can modify your material. However, for silicon, the problem is that the energy deposition tends to saturate below the damage threshold, which means that if you try simple strategies, basically the material is impossible or nearly impossible to modify, actually. Okay. Now we come to the state of the art on this. So on filamentation in silicon, there have been many papers from the last decades, including some papers on the propagation. So this relies basically on the nonlinear Schrödinger equation, where they have, I won't go to the math, of course, here, but they have some term for diffraction, one term for Kerr effect, for multiphoton absorption, two in that case, and for plasma absorption and defocusing. And at the same time, they solve the ionization here, considering only two photon absorption at first. And the results they obtained at that time is that if you use those conditions here, they can make some calculations and observe directly. So this is the electron density as a function of the input pulse energy. And they can observe a saturation, the saturation of the electron density, which can be produced inside silicon. So this reproduces actually what I told before on filamentation. And you can note also that this occurs at relatively modest input energy. Here we are speaking about like a few tens of nanojoule, and this is sufficient. You're already in the saturation plateau. And what they also did is calculate the volumic energy distribution. They tried different wavelengths. So instead of considering only the two photon absorption regime, they concentrate on like multi-photon absorption regime, take the data from the literature on the absorption coefficient, And what they observed is that there is the existence of a peak around 2 micron wavelength, which results in a peak in deposited energy per volume. So this is pretty interesting for designing applications. I will show this a bit later. And also they noticed that when you go to very long wavelengths, it tends to increase. Why is that? Well, it's related to the free carrier absorption. So the inverse Bremsstrahlung absorption. So the carriers absorb more efficiently the laser at longer wavelengths. So this is given directly by the Drude model. Okay, we can do, I mean, besides the math, we can do, of course, some experiments. And what has been achieved to characterize filamentation in silicon is first some imaging. So what they did is like classically some pump probe imaging. So this is this Russian group, Kononenko and colleagues, where they did some interferometry during the pulse. And with that, in a pump probe way, they were able to discriminate the contribution. So here you get the refractive index change as a function of the laser path energy. And by doing that, they could discriminate what comes from the Kerr effect, so the positive refractive index change, from the plasma effects, so the negative refractive index changes. You can also do some shadowgraphy, so not interferometry, but you measure what has been absorbed by the plasma. And if you do this after the pulse, basically you can see some saturation here on the transmission. So this is also consistent with the intensity clamping. So when you check the transmission of your probe as a function of the input pulse energy, you can see that you reach a plateau in the transmission, which means that there are some self-limited underdense plasma, which are produced in the bulk of silicon. Another way to do so is to carry out some nonlinear propagation imaging. So this is what we do in my group. Actually, basically, this was done in this reference for water and in this reference for the electrics. But this technique is extremely powerful in silicon because you cannot easily damage the material. So what are we talking about here? So basically, you got some femtosecond pulses, which are then focused by this objective lens here, focused in the bulk of the material, and then you get this microscope here relying on an objective lens and a camera to basically get some cross-section at different planes of your beam. And with this, you can access to the 3D fluence distribution of the how the energy is deposited inside silicon. And this is the kind of experimental images you can get here. So without going into the details, so these are the fluence distributions for different input pulse energies before the light enters the wafer. And with that, you get a direct access to the maximum fluence inside silicon, but experimentally this time. And what you can see is that you follow here, so the peak fluence as a function of the input pulse energy. You follow a linear trend first, and then the fluence again tends to saturate, which is consistent with everything we've seen before. Okay. So these were the limitations. Question now is, can we bypass those limitations? Can we circumvent them? Can we find some smart ways to deposit more energy inside the material? And there are a couple of methods which have been developed in the past. The first one is called hyper-NA for hyper-numerical aperture. So this was demonstrated with liquid immersion lens. So basically, you use those liquid objective lens with an index matching liquid, so an oil typically, and this tends to increase the numerical aperture of your objective. So normally it should be below 1, but because of the oil and because of this formula here, then you get more than 1. So typically you can reach here in this example where they could achieve some lines inside the material. You can reach more than 1, so 1.25 in numerical aperture with femtosecond laser pulses at 1.55 micron wavelength. Can we do even more? Yes, we can. How can we do that? So this was a work we did with my former group in Marseille, France, where basically we use solid immersion lens. So how does it work? So the idea here is to focus light at the center of microsphere, 1 millimeter sphere. And by doing this, basically what you do is to kind of suppress refraction at the interface, because then the wavefront here has the same shape as the surface of the sample. And then by doing this, the effective numerical aperture which you have is basically the linear index of silicon times the numerical aperture of the objective. And because silicon is a very highly refractive material, then you can reach around 3 in terms of numerical aperture, which is extremely high. And this was this made possible the production of different modifications inside the spheres, and this was like repeatable modification. So with extremely short pulses, like 60 femtosecond. So this was for the first solution. The second is to rely on surface seed. So you want to modify the silicon wafer internally. Then first you rely on something on the surface, and this is an early study from Peter Hermann and Stefan Nolte about this, where they deposit some oxide layer or some amorphous material. So this was also done with amorphous carbon on the top of your silicon wafer. And with this, you can modify like the subsurface, like typically a few tens of micron below the surface of your wafer. And with that, it was possible for them to inscribe some waveguides inside silicon, in the subsurface of silicon, I should say. And if you want to rely not on something on the front surface, but something on the back surface, then you propagate throughout your material. And what happens is that if you try to process your wafer on the backside directly without any strategy, any specific strategy, then what's going on is that the damage formation or the modifications appear in a random way. So this is totally unpredictable. So they tried here same conditions, like the same conditions, and sometimes they see some modifications, sometimes they don't. And how to bypass that? Well, you can basically metallize the back surface, and the metal will act as, like, the metal contains some free electrons already. So this is quite good for absorbing, for locally enhancing the absorption at the backside of your material. And by depositing some thin metallic films, it was shown that deterministic behavior was found on the production of modifications inside the material. And well, you can do, if you don't want to use thin films, you can just use some bulk material like copper. And this was also observed by our group in Jena, that you can basically modify the interface between silicon and copper just by focusing the light at this interface. And what was observed here is actually from, I won't go to the details there, but there are some random spectra, and you can see some copper on the silicon wafer and some silicon on the copper sample. So basically there is some mixing and melting of both materials together. Okay, another easier solution would be to use the nanosecond regime. So not use ultra-short laser passes, but way longer passes. And what happens in that case, I mean, the idea of this regime is to decrease the propagation nonlinearities that we introduced before. And this works pretty well, actually, because then the modifications become repeatable, as you can see here from this group from Netherlands. Okay, use the arrows. And the problem and both the beauty also of this regime is that if you want to understand what's going on in the nanosecond regime, then it's a multi-scale modeling. So like propagation, ionization, thermal effects, mechanical events, and recrystallization all potentially occur at during the pulse. So this is way more complicated to understand. But still, this American group here did that quite recently, and they obtained some nice results to explain like the shape of what was observed experimentally by this group here. Also, one specific aspect of the nanosecond regime is the wide variety of the material changes you can observe. So here, this is like Japanese like observations, and what they observed is you can see on the same side. So you shine the light, the silicon becomes modified. And depending on where you look, you can find some high pressure phases, some voids, some dislocations, some cracks, some hydrostatic compression strain, some polycrystalline features. So there is a whole zoo of different modification types. And this is confirmed. So this is at the nanoscale with like electron microscopy and electron diffraction. And at the micro scale, what you can see here, this is like one shot or multiple shot on the same site. And this is like amplitude imaging and phase imaging. So this is what we did with my group in Marseille before. And you can see a coexistence of positive refractive index, so positive phase, and negative refractive index, so negative phases, basically. So this is not the best. I mean, it works, but this is not the best when you want to control the modifications inside silicon. So then the idea, and this is actually the next point. So instead of using nanosecond pulses, which are like 1 million times longer than the femtosecond pulses, then why not using the picosecond regime? And this is the missing link. So yeah, the reasoning is the following. So basically, femtosecond pulses, it doesn't work. Nanosecond pulses, it works. So there should be something in between where it works, but with more control on the modification you can have. And then you got to face this trade-off between the propagation linearities and the heat-affected zone. And this was first studied when you checked here, you get the modification probability as a function of the pulse duration. And counterintuitively, I would say the modification probability tends to increase when you increase the pulse duration, which is not something normal for people working in glass. Normally, when you go to shorter pulses, then the intensity is higher, so you should produce more easily some modifications. In silicon, the trend is opposite, so longer pulse durations are beneficial. And this was extensively studied by the group of David Grojo in France, where they tested different pulse energies, different pulse durations, and they concluded that there are some conditions for which the modifications will appear systematically, like in a repeatable way. And what they concluded is that around 10 picoseconds, they found some lowest modification threshold. You can find also some fun behavior when you use single-digit picoseconds. So this is what we did with the same group actually in France. When you plot the damage probability as a function of the input pulse energy, let's say we start at high pulse energies. Okay, it's good. We are at 100% damage probability. Then it starts to decrease when you decrease again the pulse energy. But then when you decrease it further, the modification probability tends to go to 1 again. And this is due to the nonlinear propagation aspect. So this is, I wouldn't say chaotic system, but close to, at least. And then, of course, if you lower the energy too much, then of course no modification will be produced in the bulk of silicon. And yeah, another strategy consists of using pulse trains. So instead of one single femtosecond pulse, you can use 2 pulses. So this is what this Japanese group did. And basically the idea is with the first pulse, you have some underdense plasma formed in the bulk of silicon. And when the second pulse arrives, it hits the free carriers quite efficiently, actually. And this is what they observed. So these are modifications inside silicon for different delays between the pulses. And with this idea, instead of using 2 pulses, you can use multiple pulses. And this is what so you said, you know,
Yeah.
Andong Wang. So what he did when he worked in the group of David Grojo in Marseille, the idea is to use terahertz repetition rate bursts. So a pulse train at a very, very high repetition rate, intraburst repetition rate. And the idea is to provoke some carrier or heat accumulation on a pulse basis before it can diffuse away from the point where you deposit the energy. And by doing that, they could achieve some repeatable modifications as well. Finally, another way is to use temporal imperfections. So typically illustrated here, this is an autocorrelation trace. And instead of a perfect Gaussian, you get those side peaks, which are related to pre or post pulses. So this works, I mean, the idea is kind of the same. So you use poor time contrast. So then it produces satellite pulses, and then there is a pre-plasma that can be heated afterwards. It was also observed by Andong Wang that when you combine nanosecond or picosecond pulses with a femtosecond pulse, you can achieve some modifications. And in my group, we used high order dispersion to do some transverse writing, which I will talk about later on. And to conclude on those methods which have been found for modifying silicon internally, well, basically every single technique has some pros and cons listed here. So so for each line, each row here, here are what the industry would need. So some 3D process with a limited heat affected zone, a contactless method in a monolithic material. And well, if you use typically like this spherical approach or hyper-NA, then it's not 3D, it's not contactless, but it has limited heat affected zone, and this works in monolithic silicon. I won't go to the details of this table here, but basically, like you can see that every single solution has some advantages and disadvantages. Okay, and then let's shortly discuss about the applications on what can be achieved in silicon. So with these techniques, what was demonstrated, which is kind of a nice proof of concept for the industry. So the first application is related to information technology, so data storage, and the idea is to modify the material to encode information and then to read it with infrared microscopy afterwards. And this is what we first demonstrated with my former group, that you can write in a deterministic manner some information. So very simple here. But this is kind of a nice proof of concept for discriminating some modification on the surface of a silicon wafer and in the bulk. And by reading it at different planes, then you can store some data. And then this was further studied with the terahertz Earth solution for the in-volume multi-layer encoding. So here you can see they write the name of their lab at different planes, and they read it also at different planes afterwards. You can do even better, and this is what the Turkish group of Ilday at that time did. So basically, you can write some Fresnel hologram in the bulk of silicon. And by observing it at different planes, then you can see this rotating rectangle at different planes. So this is nice for holography. Another interesting industrial application is wafer dicing. So for applications in microelectronics and photovoltaics and so on. So this is what Hamamatsu, so this Japanese company, calls staff dicing. So basically the idea is that you have a whole wafer, you want to cut it into individual chips. So this is what Zhen-Ze you worked on, at least in glass, probably later in silicon. So you modify internally your wafer, then apply just a bit of pressure, and then you get those micro chips with a very nice edge here. So basically the modifications you produce with the laser serve to weaken the wafer internally, and this is done typically with nanosecond pulses, and you can separate it into individual chips. And then when you apply the force, then the cleaving is along the laser inscribed line. So you can have a fancy design even on what you want to cut. And compared to standard method, here is what you can obtain. Like you cut your wafer with a blade, so blade dicing. You can see those debris and so on. This is not too good for some applications, especially in microelectronics. And when you use laser ablation, so on the surface you ablate, then there is some redeposition of debris and so on. And this is not too good for microelectronics compared to this. So the fact that here the modifications occur internally is kind of a very advantageous situation for the industry. Okay, another application is waveguide writing. And the idea is to do some like micro telecommunication, I would say. So typically quantum applications like quantum circuitry written inside the bulk of silicon. And this was achieved this is what we achieved with my former group, where with nanosecond pulses, where we observed that it is possible to get a positive refractive index change. And it is also possible to write transversely some straight and curved waveguides inside silicon, and this was demonstrated by this American group from Kansas with some, let's say, acceptable losses, given the fact that this is the very first object of its kind in silicon. You can also, if you don't want to rely on positive refractive index, so those green gradient index on the left, you can also rely on negative index change. And instead of writing a positive index change, basically you write a cylinder of negative index change. And in the center, then the refractive index is higher, and then this is waveguide. And this is what they demonstrated in Turkey with nanosecond pulses with way lower losses. And the advantage of that is that you can have the size, like the size of your core is totally adjustable and quite easy to adjust. And finally, you can use femtosecond laser pulses, but with surface heating. So this is the study I mentioned with Peter Hermann and Stefan Nolte, where they deposit some thin film on the entrance surface, and then they obtain some subsurface waveguides. And also, if you rely on the exit surface, then you modify. This is what was done in my group. We can modify the back surface of the wafer and then pull the modifications. And for different conditions, it is possible to get some waveguiding effects. Okay. And besides the waveguides, well, there are here, I won't go too much into the details, but you can write not only waveguides, but other optical functions inside silicon, which include those waveguide junctions, so those Y junctions. So basically, the idea here is to write some waveguide and then to separate it, so you can have at the output, instead of a single beam, you have two beams. You can use, as they demonstrated in Turkey, some Fresnel zone plate to write some lenses to transform your silicon wafer into a lens. And you can also write what we did in Marseille, and this was done also in Japan. You can write also some lines inside your material, and these lines will act as a refraction grating. Okay, I guess. Okay, yeah. A couple of more slides. Yeah, another application which was shown by the group of Ilday in Turkey is microfluidics for applications in lab-on-a-chip, so basically microbiology, and microelectronics as well for cooling chips. And the idea here, what you see is a pre-modified wafer where they wrote channels inside the wafer. And then with a thermal camera, they measure the temperature of the chip, of the silicon chip. Here is what you observe under, like with your eye. And what you can see here is that when they inject some cooling liquid, then it is possible to actually cool down the whole wafer, which is quite useful when you want to do some overclocking of microprocessors or integrated circuits. And yeah, finally, you can also do some surface structuring by doing some laser irradiation and chemical etching, so LICE. So the idea here is to modify internally the material, then do some chemical etching, and then what you reveal after the chemical etching will depend on the properties of the modifications you wrote inside the material. And what was observed by the Turkish group and also the French group is that when you have negative index change, then you get porosities. So this helps the etchant penetrate inside the wafer. And when you have positive index change, then you have some material densification locally, which prevents the penetration of the etchant. So in the end, you get some bumps, some heels produced on the surface of the silicon wafer. Yeah, and finally, you can also do some backside nanostructural amorphization, and this is what my colleague Markus Blote in my group recently did. So by using picosecond pulses, he showed that it is possible to write some tracks on the back surface of the silicon wafer, and these tracks can be not crystalline, but here amorphous. So you can produce amorphous silicon on the backside of the silicon wafer with some nanostructures as a bonus, some nanostructures forming onto the backside of the wafer. And yeah, the very last application here consists of laser welding. So the idea is for microfabrication, astronomy sensors, and so on, to use picosecond laser pulses here to pre-compensate for the nonlinear focal shift I introduced at the beginning of my talk. and then to relocate the energy deposition at the interface between silicon and the metal. And when you do that, then you can achieve here, this is a silicon workpiece onto a copper plate. So you can do some silicon to metal bonding in the end. You can also extend this to the silicon to silicon configuration when you put some metallic nanolayer at the interface of both silicon workpieces. And what they did finally in France is that with nanosecond pulses, so here, here is a welding they did between silicon and gallium arsenide, and they could hold the laser which was used to do the welding actually. So like it's a few kilograms, but you can hold it with such a piece. And they demonstrated different, like welding in different situations. So silicon, gallium arsenide, and gallium arsenide with very high bonding strength. So more than 10 megapascal. Okay. I'll come to the end of my talk. So to summarize, basically, what I want you to keep in mind after this talk is that filamentation dictates propagation and energy deposition inside silicon, and it is a major hurdle for the production of permanent modifications inside the material. There have been multiple techniques which have been developed to bypass those limitations. So hypernumeric aperture, surface seeds, picosecond, nanosecond pulses, or use pulse trains. And with these techniques, well, there was some progress on some applications which could be developed inside silicon for data storage, wafer dicing, optical functionalization, and so on. If you want to know more, because that's a lot of information in the end, if you want to know more about this whole topic, I recommend this review we wrote with different colleagues. This review paper on laser writing inside silicon, and the corresponding book chapter in this recent book. So those are typically available on ResearchGate. And finally, I would like to thank you all for your kind attention.